We start with the Bessel equation that we got from when we consider the eigenvalue problem or the orthogonal set. So basically, we rewrite the equation to the form in 14.41, right? 14.41, but in this case, we probably want to rearrange that to get it to the form the same as what we did before, because I mean the 14.41 already divided by rho square, so you probably want to restore that. So you have rho square, d square, d rho square plus rho dd rho, and then you have a rho square term. Yep, actually the rho square k square term. So with the other side and the positive, so plus k square rho square and minus mu square. Okay, and that is operating on the Bessel function is either j or y. They satisfy this kind of this form of equation, right? That is the original Bessel equation, and this kind of equation, like when we talk about the PDE, the separation of variable method, this is coming from like using cylindrical coordinate. Whenever you have a Laplacian operator, most likely you get a Bessel equation for the radial part for radial coordinate rho. And this mu is coming from the azimuthal part. So if you have you including all the azimuthal angle, then the azimuthal part is proportional to e to the I m phi. Phi is the azimuthal angle, and m is all the integer, including 0, right? And so, this mu becomes m squared, becomes an integer, so that the Bessel function becomes integer order. Okay, so that is usually the case. You include all the azimuthal angle, but sometimes if you restrict your azimuthal angle, then this doesn't have to be an integer. It can be any real number. If you still use trigonometric function, then it's still minus mu square, but maybe a real number, a fraction, right? But that is fine. It's still the same equation, but also you can have an option that not using trigonometric function if you're not including the whole 2 pi angle, like you use a exponential function in phi, then this becomes instead nu square become cos nu square. That is possible, but we usually not consider that case. In that case, you consider that the Bessel function, this nu becomes an imaginary number, so this order becomes imaginary. But we won't go to that. But we consider the other option is just this k square. This k square, and for this j nu, well, assuming this is a positive, so you have a positive k square. And the reason you have positive k square is when you use when you consider z part of the separable solution, you use either exponential, so you have exponential kz or exponential minus kz, right? Then if you use exponential function, then for the radial part you get the positive k square here. Okay, now that you can change. You can sometimes more convenient to use e to the I kx kz or e to the minus I kz using trigonometric function in the z direction. For example, you do a Fourier transform of the z part of your solution, then the Fourier transform require you have a ik, right? You have this kind of form in the Fourier transform. Then in that case, this k square will need to be negative, right? And so, so in that case, you can say change that to minus sign. This becomes plus sign. The new square is still positive, so both terms becomes positive. So you have a negative sign. Then if k square is negative, it means the solution is still the same, but you need to change k. You need to change k to ik, right? So that this ik square becomes negative. Okay, and using a positive k, ik square becomes a negative. Okay, and so in some sense you can just say we can still use the same Bessel function j, but using imaginary argument. That is one option, but sometimes causing confusion. So most people would like to define another function for that. Okay, so that is what we call the modified Bessel function. This equation becomes a modified Bessel equation. I mean, this operator, whatever this function is. Okay, so this is the equation. This would be equation 14.97. This 14.97. So the difference is this terms, right? For the ordinary Bessel equation, you change the sign of this term. For modified equation, is of this form. That's okay. So that's the only difference. And now the idea is we want to redefine this. So this we can at least one of the modified Bessel function we define that way. So this I nu, one of the two modified Bessel function that will define as argument. Real x argument is defined as I to the minus nu is nu I times x. So that's the definition of this I. Okay, basically of this form. So change back k row as x as a real number. Right? So x is a real number, you multiply by I, so this becomes purely imaginary argument. And then we define I here, and this factor I to the minus nu is to make it real. So that becomes a real function. To see that most easily is you can use the series solution of J, right? Series solution of J is in section 1, right? Section 1. Let's see. This equation. So equation 14.6. So you can substitute that in equation 14.6. And then you have carry this I minus nu here. And then the J is summable S from 0 to infinity minus 1 to the S power S factorial gamma nu plus S plus 1. And then now the X part becomes IX plus 2 and nu plus 2S. Okay, and now you see why you have this I, because it's I to the minus nu power, because it will cancel this I to the nu power, and you still have this I to the 2S, right? I to the 2S, but I I to the 2s is I squared to the s power. I squared is -1. So -2, you have an extra -1 to the s power, but you already have a -1 to the s power here, right? And so -1 times I'm going to get you 1, so 1 to the s power is just 1. Basically, this cancel with the minus I to the 2s part. And then I to the new cancel with this factor, right? I to the -2 that we define for this function. So altogether, you get just get rid of this -1 to the s. So this give the solution oscillatory behavior. But now you get rid of that. Altogether is just you have s stereo plus s plus 1 x 2. Basically get rid of the I plus 2s. Okay, and you see that for real x is always real. So x to the new is real. S is just the summing of the integer. So this is real and positive. All this power real and positive. And s factorial always positive. The gamma function, if for nu is greater than, so this s is from 0, right? So the s is integer, positive and 0, positive integer 0. And if nu is greater than -1, this is also positive. And so this I nu is always positive, and also has a behavior that it will grow indefinitely for large x, because this is the behavior is like the exponential function. So if you know that the exponential e to the x is just summing over x and factorial, right? So modified by this gamma function, but asymptotically it will grow like exponentially in this situation. And so that's the behavior of this I function. Is that okay? So that's basically it as a definition. And there's one way to get to this one. Another way to get to this kind of consideration is you can use the generating function, for j, and then substitute it in the integer imaginary argument for j. Then you get the basically you get the generating function for I, and so that would be the homework problem. So you can it's very straightforward. Okay, and now what else for I? Now for I, for the small argument, let x goes to 0, then you can see that it's well behaved, because all the j function are well behaved, and for small x or for positive nu, for positive order, because it's x to the nu, so it's well behaved. And usually we define I sub nu to be well behaved at the origin, and the leading order is just this x to the nu and set s to 0, right? So you have s is 0, s factorial is 1, so you have gamma to the nu plus 1 times x over 2 to the nu power, and that would be the small x behavior in the equations 14.100. And another property is that I sub n. So this, the j sub n and j sub minus n are linearly dependent, and likewise I sub n and I sub minus n are linearly dependent, just because it's imaginary, defined as using imaginary argument. But using the same consideration, you can see easily that you get rid of the -1 to the power n dependency. So basically they are the same. I think this is also a homework problem. You can show that quite easily using this definition. Okay, and likewise, you can also modify the recurrence formula for I. Right. So for modified Bessel function, that the recurrence formula is slightly different, and due to exactly the same kind of consideration, because if you have this x, you have this I factor, so then you introduce some sign change for in the recurrence formula. So that is, I don't know whether that is a homework problem. So it's 14.104 and 105, but either way, it's very straightforward to divide that. Using the recurrence formula for J, you can find out the recurrence formula for I, and I think the end result is just that end result is just changing the sign of the two terms. So u minus 1 depends on x. And the Bessel function, this is a positive sign, plus. But for I, it's different. And later on, we'll introduce another Bessel, modified Bessel function, k. And we'll have another recurrence formula, slightly different recurrence formula. Not the same as I. So that is, for modified Bessel function, you have two recurrence formula for I, and one for I, one for k. So I sub u. Okay, and then the other one involving the derivative is change sign to plus sign. I mu. Okay, so so those are fairly straightforward. You can get this too. Okay. Is that okay up to here for I? So now we'll talk about k, and k we define it differently. So for I we use j sub nu, and because j sub minus nu is the linear independent solution relative to j sub nu, you might think you define another one for another modified Bessel function using j sub minus nu, but it's not the case because we want to get another function that has the different asymptotic behavior than the I function. I is, for large x, is exponentially growing. It is the leading order behavior exponentially growing. And then we want to have another linearly independent solution that is exponentially decreasing for large x. Okay, and so that's the reason we define this k function. And to get to that, the easiest part is to find a solution that has the asymptotic behavior, like for large x, say, for if either I x or I to the minus 16, and choosing a negative imaginary or imaginary argument. And it turns out for exponentially decreasing, that if you have an imaginary x, that you have I times ix, that will give you e to the minus x. That will give you the exponentially decreasing behavior for large x. Okay, so that is what we want. We want a Bessel function that is asymptotically has a behavior as a real for real x argument, but this becomes complex into the ix using the Euler relation. This is like a cosine x plus I sine x. And we haven't talked about the asymptotic behavior for j and mu, j and y, but later on, next section we'll talk about that. But j has the behavior as cosine, and the y has the behavior as sine. This basically is j plus iy, this behavior, and we define that as the proportion to this h1 function, right? So we'll basically jump ahead, assuming that the asymptotic behavior of H1 is like that, which we'll talk about that in the next section. So, we'll use that fact to define this K function, right? So to define differently than the I function. So the K function is K nu x is defined as more complicated than the I function with this extra pivot to factor in front, and then I to the nu plus 1 power h nu 1 imaginary argument. That is the definition of K. Is it okay? So all these are factor in front as for convenient. So, okay, then assuming that the H1, the asymptotic behavior will be proportional to e to the ix for large x, and we assume that, but we can only show that in the next section. But anyway, we can carry on with this definition. Like just treat it like a definition. I mean, some people define it slightly differently, but therefore, most common use is defined like this. And then we mainly use as a complementary to the I function. The I is exponentially growing. We want the exponentially decreasing function. Right? And then now we can substitute the definition of H. So 2 I nu plus 1. And then you have the J function. H is defined by J plus I y. J nu I x plus I y nu over imaginary argument. So that's how we define that. And the one thing automatically, obviously, this one is proportional to I, because I is defined by this kind of behavior. But you have extra term in Y. So the first thing changes the small x behavior. For small x, J sub nu is regular. So this would be all this. Just mention that is x to the power nu, but then y is not, right? We consider that in the y function. So for non-zero nu, it has this x to the minus mu behavior, that's small x. So it's still, when you use imaginary argument, you still have the singular behavior. It doesn't change. It's still going to be large. And for 0 order, y sub 0 has the log x behavior, and it's still singular. Even your log ix, you can treat it like a compact function, and it's still the logarithmic singularity. So the difference between I and k is like that. So I is regular near x equals 0. K is singular near x equals 0. I is exponentially large at infinity, and k is exponentially small at infinity. So these are the basic property of I and K's, and when you consider which one to use, basically you're using this kind of consideration. It's okay, so that's the most important thing. All right, and then we can further we define this K using the I function. The relationship relate K to I, K sub nu to I sub nu. by because this is already proportional I sub nu, but not y sub nu yet. We can do that by using the definition of y, right? And the definition of y is in section 3, 14.3. You need to go back to that. And in equation 14.57, we're basically now we keep doing that. So copy this coefficient in front. I mean, all these will eventually this factor will make the k as a real function for real argument of real x, right? And hopefully we'll see that. We have j nu y x here, and then I using the definition 14.57 is you have a cosine nu pi and j sub nu x, which is I times x in this case, and then minus j sub minus nu ix, right? And then divided by sine of nu pi. Okay, and so altogether you need to group the two terms, right? You use the common denominator, sorry, so, and this becomes a sine nu. This is just write out. So pi over 2 I nu plus 1, and common denominator nu pi, and you have a sine nu pi plus I cos nu pi times c sub nu x minus c sub nu minus nu x. Okay, and this one is an exponential function, right? Because finally we so we erase the j because j and I are related to that. Let's write out I because finally we want to relate to I. So I nu is I to the minus nu j nu to the ix. I mean ix argument. This is how we define I sub nu. And now the problem is to relate this one nu is 14.106. This is j nu plus I y is minus this one, and then sine common denominator sine pi nu, and j minus nu is There's a minus sign, right? Which? I just, yeah, there's an I, right? There's an I in here. There's an I in here, right? There's an I in here, right? And yeah, right. So that there are two terms in this 14.107 to eventually relate to I new. So let's consider the second term. It might be easier. So you have I. Finally, it's I. You have I to the new plus, or you can write like here. So this is I sub new, right? So you can say I sub minus new x will be because change new to minus new, so I to the new power j sub minus new to the ix. So we have j sub minus new to the ix. Now you have I times I to the new plus 1, right? So I to the new plus 2, but I squared is minus 1. So you have a minus is minus is 1 positive, and your I new times j minus new to the j minus new and argument ix. And so the first, this multiplied by all that becomes just a positive sign. So it's just right. At least the one term, we got it. And the first term is just I sub minus new x. Right? Using this definition, right? This minus I multiplied by the other side. I times I is minus 1, cancel the minus 1 I new j sub minus new. This one give you I sub minus new. Okay, that's the first one. And the second one is a little tricky, more tricky. And you can pull an I out, pull an extra I out, and this become minus I. This become e to the minus I pi. The second one is, let's copy everything. You have I new plus 1. And what you said is pull I out, so it becomes plus 2. And then the rest is cosine nu pi minus I sine nu pi, which is exponential function of minus I nu pi, right? And the rest is j sub nu ix. Okay. And then you use the fact that e to minus I pi is just minus 1, right? So this is minus 1 to the new power. Minus 1 to the new power. Well, minus 1 is I squared. Minus 1 is I squared. You can see I to the 2 new. So basically, right? This right? E to the minus I nu pi equals to e to the minus I nu, right? Equals to e to minus I pi is minus 1, which is I squared. I squared, I to the 2 nu power, right? So this is I to the 2 nu, and then multiplied by I to the nu plus 2. But then did I do it correctly? I mean, this, Probably we can put a minus sign here because we need a minus sign. E to the minus I pi nu pi is e to the I pi minus nu. And you can say that all this complicated is I to the pi over 2 square and minus nu because minus 2 nu. E to I pi over 2 is I to the minus 2 nu. Okay. And so combining with this, you have I to the nu plus 2 and I to the minus 2 nu. So cancel one of them, so it becomes I to the minus nu. And plus 2 is just minus 1. I to the 2 is just minus 1. So minus, this is minus I to the minus nu multiplied by j nu, which is I nu. Okay, so finally, we get the I nu x minus minus I nu. This I minus nu x I nu x divided by sine nu pi. Okay, so that is 14.107. Okay, can you see that the second one? The second one is I didn't write all the details. So basically transform this factor, this factor, and transform the I to the minus 2 nu and multiply by this one. Using the fact I square is minus 1. And I 2 nu times I to the minus 2 nu, I to the minus nu, which is, and multiply by that, give you I capital I sub nu. Right, there's too many I. The imaginary number is I. The function is also I. Right? Okay, so finally we got that. So the reason we went through that is to see that this is a real function. Okay, after you do all that, because you define with I to the power nu plus 1, so that is not apparent that is complex. Also this H function, and all that make it possible to be complex. But after we substitute all the definition, finally you get to this form. And this form explicitly real because we define this I as real function. And this sine function also real. Right? And then it has this similar dependency like the y function with this sine nu pi in the denominator. But so for integer order, you did do the same kind of limiting process to define case of n, or n as an integer. But that can be done because we have already done that for the y function. That can be easily done. You can do that or go back to 14.106 to do that. And then the rest is to write down the recurrence formula for k. So it's different again from I. So for k is the first one is similarly you have to change this minus sign. But then there's another sign change on the right hand side. It's minus 2 nu over nu. It's different from I. Again, because the right hand side also changed sign. And the second one is plus equals to minus, and you have a negative sign here. So, and to derive that is also fairly straightforward. You can use the recurrence formula for the Bessel function and the definition here, like here to define to derive this recurrence formula. And the next one is this small x property, and which is coming from the y, small x property of the y function, which we already consider. Just write out explicitly. You get the two kinds. So one is whether the order is 0. So y sub 0 has the log singularity. I sub nu for non-zero nu has this power x to the minus nu. So that's the two function, two equation, 14.110 and 111. Okay, and now the next two equations are the integral representation for I sub 0 and k sub 0, which we had that in the h function. I think we have the similar form in the h function, right? That is from no, not the way the y function, y and I mean, I think the text will only write down the y, but in the lecture I think I wrote down the k. So 14.63 for y sub 0, and there's similar similar integral for j sub 0, and together you can write down the asymptotic. I mean the integral formula for this I and k. And that would be equation 112 and 113, right, for I sub 0 and k sub 0. And I think one of them, or at least one of them, or both will be an exercise, right? And then that can be derived using the Hankel function, the integral representation of Hankel function. So I'll leave that as exercise, right? And